So I'll just first introduce our first speaker, Viresh Kumar Patel. Uh, he's going to present on US-India Federated Testbed Impact Analysis of Communication Rate on TND co-simulation during the fault. And Viresh actually is doing his PhD in Electrical Engineering Department at Indian Institute of Technology, Kanpur, and he works on the state estimation, parameter estimation, fault analysis using the data analytical methods. He completed his Master of Technology at VJTI Mumbai, and he did his bachelor's in Electrical and Electronics Engineering from Rajiv Gandhi Pradyog Vishwavidyalaya. So he has a different experience so working on different projects, and also he has a teaching experience in the past. So he has a overall experience in both the research projects as well as the teaching. Then I'll go to the next speaker. Let me just introduce quickly Javier. So he is actually going to deliver the talk on modeling of AC microgrid with the DER for protection in distribution grid operation by simulation analysis. Um, Javier actually received his BE degree in electromechanical engineering from University Privada Boliviano in 2013, and MBA with emphasis in power and energy sector from same university and 2016, and MS degree in energy system engineering from Texas A&M University, Texas in 2017. He's working towards his PhD in electrical engineering at Texas A&M University, and his current research interests include microgrid, distribution grid protection system, relay scheme, design, distribution, distributive energy integration, DC, AC, inverter design control, and grid control monitoring and operation, protection schemes, relay design, mathematical optimization, okay, and so on for the power system. Um, Now I'll invite our first speaker, Viresh Kumar Patel, to just deliver his webinar on the federated co-simulation between WSO and IITK. Viresh, you can just start sharing your screen and present it. And you have almost like 25 minutes to cover the presentation, and thereafter like Javier will start his presentation, and then he will give like at least 5 minutes at the end for Q&A. We'll take the Q&A at the end, and feel free to drop your questions in the chat. Thank you.
Is it visible on full screen?
Yes.
Okay. So, hi, I'm Viresh Patel. I will be presenting the work of US India Federated Testbed Impact Analysis of Communication Rate on TND co-simulation during the fault. So, here the impact of data rate on the TND co-simulation was performed, and where both the simulators were as far as possible. One was at IIT Kanpur campus, and one was at the WSV campus. Now, the overview of the presentation would be like co-simulation and its need will be discussed in the first, then the problem which we have addressed, and then the system and the concept of the TND which we have implemented, and Vilas framework, then the Vilas framework which we have used to communicate data between the two RTDS is mentioned, and the co-simulation with different data rates and its results are presented then, and then the conclusion and the future work will be presented. The co-simulation is simple, the coordinated execution of two or more models in different with that differ in different representation and with different runtime are combined and executed coordinately. So you can see here that different kind of simulation are there. So the classical simulation is there is one solver and one model, and in the parallel simulation there are two solvers and one model is kept run in between both. And in co-simulation both solver is different here, and model one is simulated over there, and model another solver is there, and another model is simulated there, and they are both combined. So this is a co-simulation, and need of the co-simulation is basically due to the like hardware constraint. Like if suppose some model which is larger than the hardware constraints. So it can model larger system. So one of the need is to model the larger system. Then another is to model the interaction between different entities which are geographically located apart. And another important is to model the communication layer over the power layer. So the software for which power layer is like RTDS, and for the communication we will be using different software or solver which is more appropriate for the communication layer. And they both will be combined using the Vilas framework or any other framework. And another part is using different model software to model different components. Like if suppose there is a some software which is more compatible, more accurately modeling the DARs. So it will be used to model the DARs of the systems, and another all the other part will be simulated in another software. So it can be combined. And another now the problem which we have addressed over here is we have simulated transmission distribution system and analyze the different data rate which will be to simulate the fault, and then and find the optimal data rate at which fault can be simulated in the co-simulation of transmission distribution. So simulated, then the optimal data rate will be used to simulate another distribution events like load switching and high impedance fault. The concept and the system used for the TND co-simulation was that we simulated two systems. One was IEEE 14 bus system, which was simulated at IITK in the RTDS system, and one was the IEEE 13 bus system which is was simulated in WSU campus. And in IEEE 14 bus system, one of the bus 13 is modeled as a dynamic load, which will get the P and real and reactive power from the model of IEEE 13 bus, which was simulated at WSU. And the main idea is idle source transformation used for the co-simulation. So in idle source transformation co-simulation, what we do is like suppose we want to simulate the load at bus 1 11 13. So bus 13 voltage, frequency and phase is sent to the another location, like where the another simulation is running, like IEEE 13 bus system is simulated in WSU. So their voltage, frequency and phase is sent, and then the simulation is run. Then the P and Q from the IEEE 13 bus is sent back to the bus number 13 through a Vilas framework. And in this way, the co-simulation is executed. The framework for the Vilas use was like we created Vilas super nodes at both the location. The location one was WSU campus and location two was IIT Kanpur. And from the location one, the RTDS is sending the real and reactive power to the location from the location one to the location two. And from the location two, the voltage, frequency, and phase is sent through the Villa supernode through the Villa supernode at location one, and both both the communication between Villas and RTDS is done through GTNet card, and the protocol which was used for the communication was GTNet SKT protocol. And co-simulation, then the co-simulation with different data rate was performed. First, the simulation IEEE 13 bus was simulated, and the voltage, frequency, and phase was sent to the IEEE 13 bus, which was simulated at WSU. And then the real and reactive power from the IEEE 13 bus is sent back to the IEEE 14 bus 14 bus system, and then the communication is established using Vilas framework, and whole system is get on running. And then the fault was created at one of the line between in the IEEE 13 bus system, and the fault which was then reflected to the IEEE 14 in the terms of P and Q, and the load variation is captured at IEEE 1314 bus system, and the data rate which was used for a different data rate was used of are from 10 data packets per second to the 1,000 data packets per second. Uh, then the results which were captured, like when the different data rate were tested from 10 packets per second to the 1,000 packets per second, P and Q are captured. P and Q value between pre, during, and post fault event was captured at IEEE 13 and IEEE 14 bus system, and error between both are plotted in the plot you can see here. And the result was that 100 packets per second shows the lowest error. So it was selected as an optimal packet rate at which co-simulation can be executed. Then this optimal data packet rate was used for the another two event simulation, which was high impedance fault and load switching. So during the high impedance fault event, all the different kind of fault were executed and the error was plotted. And during the load switching, this was the error curve. The conclusion and the future work would be like two location having different time zone of 12 hours and 30 minutes were captured, were combined and co-simulated. So what we concluded was co-simulation can be effective tool to merge real-time simulation resources needed to simulate larger test system at large distance also. So we can simulate much more a number of DERs and much more number of buses in the system by using a co-simulation. Find effective data rate at which co-simulation can be executed at such a large distance. Finding an optimal data rate by finding the error in the data. From the then the further future work would be like it can be tested for the highly distributed resource control, which like kind of two DSO are separated apart from the geographically and can be tested in this kind of environment. And many more further work would be like course you can like simulate the communication layer over the power layer by a communication software itself. Thank you. Thank you everyone for this.
Yeah, thank you, Viresh. I think that was quick. I expect like, okay, you will cover up to 25 minutes. It's okay. Javier, you would like to start now?
Okay. So
Meanwhile,
time.
Viresh,
Yes, sir.
yeah, can you answer the one of the questions they posted in the chat?
Yeah. The timestamp which we use was 50 microseconds for the simulation. Is there any another question?
Yeah, thank you, Viresh. I guess let me Javier.
Jorge. Hello, I am here.
Okay.
Should I start now, or we will go?
Yeah, go ahead. Okay.
Okay, thank
So,
you.
Viresh, can you stop sharing your
Yeah,
screen?
I will stop. Yeah, you can share now.
In process of that. Mm,
Yeah, Viresh, meanwhile, I see the another question from Suman Biswal. He's saying, as the two systems are geographically isolated, does it affect the performance of the simulation? Viresh, are you there?
Yes, yes, I'm there. So there
Yeah.
were like a communication delay itself in this. So we have to take care of communication delay. For that, we have like get the direct connection between two RTDS using the port binding method. And with the like number of data packets we have tested, so it got that 100 data packets were the optimal data packet which was optimally simulating the correctly simulating the event on the another side. It was reflecting perfectly fine.
Yeah, thanks, Viresh. O'Hare, are you ready to go?
Yeah, I'm ready. I'm not sure if everyone can see my screen. My apologies,
Yes, we can
everybody,
see your screen
for the
presentation.
delay.
Yeah,
So
that's okay.
thank you so much, everybody, for having me here today. It's a pleasure to present in this webinar. Mm, as Professor explained before, my name is Jorge Cisneros, and I'm a PhD student in Texas University. Uh, so we will talk today about the title Modeling Microgrids with Protection in Distribution Grid. I have operation by simulation analysis. Mm, so please let me know if you can see my screen. First time actually
Yes,
I'm
so we can
using
see
this
the second
screen
slide
here.
contents, I guess.
Okay, thank you so much. I appreciate your feedback. So the content basically today we will discuss about microgrid modeling and inverter control. I will talk about IBR, inverter-based resource operation and microgrid validation. We will talk about the study case model we have, which is a 4-bus topology model. We have a conventional relay and when faults cannot be detected, fault studies for most common types of faults, short circuit type of faults, which will be short single line to ground, line to line to ground, line to line, and line to line to line fault. A little bit of relays protection and modeling schemes and identification of faults, communication and clearing time of faults. So to continue further, I will talk about the first topic, which is microgrid model and inverter control. As we all are aware, we know what is microgrid. So in a summarize, we have a microgrid that can operate, as we can see on the top figure. So we have 4 levels for control of the microgrid. We have the level 0, which is the inner loop control for inverters. We have the level 1, which is the local control loop, most common for the troop control. We have the second loop, which is the microgrid central. And we have the third level, which is the global loop control that works a grid in a big setting. So the left bottom figure shows a microgrid, which can be a grid connected and autonomous connected. We can see some margin that presents the, let me see if I can mark here. So here we can see how we represent the point of common coupling, which is a microgrid when it works as autonomous mode and as a grid connected mode. The two figures on the right hand side are exemplifying that, like a microgrid connected to the grid, and also autonomous, like basically independently, like can be in a small village in a very remote area. And the grid connected mode can be a small neighborhood in an actually very populous city. Um, Next slide. So the inverter construction, so the inverter is a critical in microgrids because inverters are used for solar PV. Basically, they convert the DC power into AC power through a set of power electronics components. So we have the two levels that are mainly most important when we are constructing a single inverter. We use the level 0, which is the inner control loop, which is in charge of the voltage output in the terminals, the current terminal, the feedback, feed-forward compensators, and we have different fault limiters and linear and nonlinear controls. The second level, which is the level 1, focuses on group control methods. Mostly they are used for load sharing, like traditional generators in a big setting of grid where we have in parallel two different or three different types of generator. In this case, can be different inverters. We control the active power to the frequency and the reactive power to the voltage. And we have a virtual impedance. So the bottom figure is showing basically an exemplification how the DC voltage comes from the sun and is represented as a DC source. And here we use the power electronics to throw a pass to a LCL filter and then to connect to the grid. So in this side, we will have a grid which is from going from DC to AC voltage. There are two methods for communication lately, which is the group control, the one we utilize, which is no need of physical communication between inverters to share different type of loads. And we have the master subordinate, which requires a bigger communication system, and it's basically like an traditional EMS or an SCADA system for the people who's familiar with them that we can control from different areas. So the following figure is showing the control of the inverter. I won't spend too much time here. I will explain later on in the following slides. But here I'm marking the most important sections because the slide's a bit heavy, so it will be very difficult to go through this one. So we know that basically here we are showing the control system shown in the previous slide, where we have the voltage and current measurements that go to the P and Q power calculation used for the droop control. From here we generate the reference voltage, and with the virtual impedance we can calculate the voltage loop control, which is in the level 1, as I showed in the previous slide. From here, we pass through the current limiter. Basically, this current limiter prevents the inverter to get burned in a case when we have a fault in the grid. Then we pass through a current control loop to later on convert again, go back to the ABC reference frame. So all these calculations were done in the DQ0 system. From here, we have also a voltage limiter, which prevents the over and under voltage for the protection of the inverter itself during fault operation. That's why I marked these two blocks in red, because they are only main use when we have a fault. So we know we have three types of inverter. So I will focus on grid forming type of inverters, which is the common in industry. It's the one we can actually buy to install for our homes. And we have also the different reference frames for doing different control models, which is the DQ frame, the alpha beta frame, and the ABC frame, which is the natural reference frame. And so the following slide is showing a little bit about the drop control and the fault current limiter, how's the operation. On the upper figure, we have the simulink control implemented, and in the bottom, I have a reference. So we can know that the frequency and the voltage value in the reference frame is shown as F and E star. P and Q are actually the output, active and reactive power of the inverter. The F and E without the star, they are the nominal angular frequency and the output voltage amplitude. We do have these two values that are M and N, which basically are the proportional frequency drooping coefficient, which is the M, and the N is the voltage droop coefficient. They are utilized for basically sharing the load between different type of inverters that have the same type of construction, like they have group control enabled. On the left-hand side, we show the implementation in a Simulink, but on the bottom, we can see basically what is happening. So we have an inverter, they have low thermal inertia. So when we have current passing through them, sometimes can be very high, and this will damage all the semiconductors and compromise the operation of the inverter. So the control basically designs for short circuit fault studies, and we consider the limit that we have certain value that prevents the signal from passing beyond a threshold value, which is exemplified in this small block, like by a saturation factor. The common one we utilize is 1.2 for inverters for construction based on manufacturer documentation. I will talk about the invertebrate resource and the degree validation of our construction. So this is a subset of our four bus system grid that I mentioned before. So basically, this test was done to validate the response of the inverter in a normal setting, like in a distribution grid, the inverter will go through different type of loads. So we try to test the most critical ones in this setting to validate the operation of the inverter itself. So we tested here as called as step load. There are different loads that can be turned on and off in the within a household. And we do have the tap load, which is a load that is happening in between a distribution line, which can be seen in the figure here. And we also tested a ramp load. Like all of them are not very common. I mean, they are commonly, but they are not like separated. So they work in a distribution grid, and they enter, they leave as they progress. So this we consider were the most critical one, and we were able to validate that our voltage is maintained in the limits based on the norms, and our current can follow depending on the load. We tested different types of loads. In this section, I will talk about the study case model. So here I will discuss a little bit about our topology, the one I mentioned, the 4-bus model with inverters. Again, like in previous slide, this is how it's in Simulink, but this is heavy loaded image, so it will be difficult to follow or it will be very extend. So I have in the next slide an online diagram, which I can explain the same thing we have here. So a better understanding for the schematic model. So we have basically 4-bus grid where we have 3 inverters and load, and we have in the 4th bus just a load with lateral feeders. We call 4-bus model because we have the operation in low voltage, like it should be done in a household or in a small neighborhood. And the distribution done is in low voltage as well, or medium voltage, depending the country or the norm utilized. So usually our voltage level in the low voltage will be 120 to 140, and this can range from 220, depending the country, either it's US or Europe. And in the distribution line, since this is distribution grid, our voltage go up to 4.1 kilovolts. So based on the literature, this is a medium voltage, but still is in the low voltage setting because it's not passing to 10,000. So it depends on the country where everyone is looking for. So that's basically the main explanation here. So we have the inverter connection here where we can convert the DC, which is a power DC source from the solar heat, which should be a inverter. And then we pass to the transformer. So this is feeding its own load, like some lateral feeder within the DG3 in this case. And this connects to the distribution line, which as we can see, this is a short type of line where we have, which now is a medium voltage, the way it's presented in this figure. And we have the different relay and the communication system here, as can be seen in the bottom figure as well. So, and in the load side, we have different lateral feeders with different type of loads. Here I name it arbitrarily like step load, ramp load, but it can be like many types of loads we have, like I presented before. For the validation process, we tested an important setting, which is the frequency and voltage, which the frequency should be always maintained as nominal. In this case, we utilize 50 hertz, and the nominal is maintained thanks to the frequency restoration implemented in the inverters. So we know that the frequency drops as we increase more loads, as it's shown in the droop control model that I showed before. But with the restoration, we can keep in the nominal, which is how it's supposed to be working in real life to guarantee operation of the grid within the neighborhood or keeping the standards. So I will go and show the left-hand side figure. Here in the left-hand side figure on top, I have three different colors. We have the blue one, we have the orange one, we have the yellow one. So here I'm showing the apparent power, which is in the y-axis, and the x-axis I have the the time in seconds. So here we can see how is the operation of bus one when it's feeding the load. We can see how happen now when we feed the load to loop control by the two different buses, like bus one and bus two I showed before, which is in orange, and we can see like an increase in the step. And in the third bus, when we feed in with the three of them, we can see how we are actually completely feeding the load demand from the whole microgrid. And this shows how we actually can share between each inverter how much power we want to give depending on the application. Um, on the left-hand side, I'm showing a more specific image where I have active and reactive power. So the active power is in blue and the reactive power is in orange. So we can see this is purely active load, but after 0.0 seconds, we add a new reactive power load, which is independent of the active. So we play with different power factors. But the important thing here is we are keeping the frequency as close to the nominal and the voltage levels. So in the two bottom figures, I'm showing the voltage and the current levels, as I mentioned before. So we can see like the voltage is maintained during the different type of events, which we have the step load, we have the ramp load, and we can have a tap load in operation. So in the following section, I will talk about a microgrid operation during fault. So we know that there is traditional protection, which is it consists of different fuses, reclosers, circuit breakers. But the industry, with the implementation of so many energy resources, renewable energy generation in the load side, we do have these common cases that were identified in the paper we presented before with the IITBBS group for part of this project. Uh, we identified short circuit capacity, sympathetic trip, unintentional airlining, blinding of protection, bidirectional power flow, integration of another TG, and relay miscoordination, and finally the auto-reclosing failure mode. So these are 8 cases that we could, after a very extensive literature review, we could identify and find in the books that do appear compared to how was used traditionally. So this figure is showing basically how is a traditional relay operation. We do have a substation here. We have different items, I can call them. So we have the breaker, we have the recloser, we have the fuse them. So basically the fuse them is the one who limits the responsible for the permanent faults downstream the line. The recloser is the one who actually operates first. So it operates in a fast mode, as we can see in the figure on the right-hand side, between the red lines. So in a fast mode, we have the operation of the recloser, which is fast enough to give a chance the fault to be clear, self-clear, in case it was a branch or in a tree. Then we have the fuse operation, but basically this operates to clear the fault. But if the fault is not self-cleared, this is when the fuse acts. After the fuse acts, if the fault is not cleared, so the recloser has a slow mode operation mode, then acts as a backup of the fuse. And as we can see in the figure, here is the slow curve model. So we have the fuse curves that come here, and then we have the slow mode curve. And the latest one is the relay. So the relay basically is the last one who operates in a case of backup, like double backup. In case the slow mode recloser does not operate or it disconnects or connects and keeps identifying the fault between the grid. So basically, the recloser in slow mode fails to operate, then the circuit breaker upstream should operate immediately as a backup of the recloser, as we can see in the figure. So we have a traditional breaker coming from the distribution level. We have a recloser here, and we have different lateral feeders constructed by different fuses. So these are the 8 types of faults we identified that are common. I won't go through all of them. We already presented a few of them, so I will just address a few important ones. So in this case, I will talk about the blinding of protection. So we know the short circuit capacity, sympathetic trip, and intentional eyelining. A blinding of protection, basically, we have a fault. Traditional way, we can detect it, but because of the reduced reach due to the microgrid integration, to the distribution generation integration within the grid, we can have a, we might not be able to see, the relay might not be able to see the fault itself, because basically the current, it's interacting with the grid or the substation and as well with the distribution generation. So in this case, it's possible that the relay won't trip, and this is actually a very big problem that is happening nowadays. And among the other case studies that I mentioned, we have the bidirectional power flow, we have the integration of DG, relay miscoordination, and auto reclosing. And same as before, I will explain the case 2 here, which is the bidirectional power flow. So as we could see in the traditional protection, we have basically a line where we have a fuse, we have reclosers, where we have also the relay, which they operate, but they won't operate in case we have a DG installed, because we will be feeding from both sides. The traditional way only considers we have feeding on one side, let's say the left-hand side or the distribution level, or it's coming from actually generation, and we just consume in the load. But due to the increase of penetration of solar panels and solar energy in DC, later DC, we can see that the faults will get affected. So we will have a double feeding fault. So it might not go detected as well. And the relays won't operate, and also know the fuses, and also know the reclosers. So I think those are important cases I could recall from here. So in the following section, I'm presenting some types of faults, the most common ones. So this bus model here is the same as I presented before. Difference I would like to address is here I'm showing where we test the different faults. So in this block in black, we're showing where we have a fault in the middle of the line between line distribution grid inverter, bus one and the bus two. And we can see all the communication that happens between them that we implemented further. And also the other line, like top line, we can say in medium voltage, that connects the DG3 with the DG4. Also has communication here, not presenting the fault, but we test the fault in different locations, like all over these different subsets of this model. And we could identify different cases, and we could validate and study the different type of loads as I presented before. So in this example, I'm showing how actually behave 4 different faults with inverter operation. We have on the top figure, we have the single line to ground fault. And as we can see, we have a small transient during the fault, but this fault is due to the controllers and the limiters. They are trimmed basically in our control. And we can see that our current is not anymore huge. So for the people who has experience with the faults and protections, we know that the current usually 7 times the fault, and it's actually very big and it's easy to detect. But due to the power electronic side and the limiters for protecting them, we don't see those waveforms in the inverter integration. So that's what makes challenging to detect traditional way. Additionally to the cases where I showed before that they do affect directly. So on the top right hand side, I'm showing the line-to-line ground fault. So actually the upper figure represents the voltage and the bottom figure represents the current. The bottom left, I'm showing the line-to-line fault. So again, all these faults are happening at 0.5 seconds, which probably I didn't mention it. And this happening between bus 1 and bus 2, which is in the previous online diagram I showed. It's exactly as it is. And going back, the fourth figure, I'm showing the triple line fault, where we can see basically the voltage and the current. And here we can see how the voltage actually goes to 0, which is expected because of the three-phase fault. But to the controllers, if we just measure the current, we actually can mispresent that there's no fault here, but we do actually have a fault. So it is, as I showed before, those are very critical cases where the responses got affected and relays won't detect. In the in the following section, I will talk about different types of relays, different protection schemes, and some detection algorithms we developed and we implemented. Some of them we pick up from the literature. Uh, we do have how are traditional and different relay types of methods nowadays. So the overcurrent protection, which is shown on the top left, is, as I showed before, we have circuit breakers, we have relays, we have fuses. That's the traditional implemented in distribution level, FUSEMAN. And we can see there is a fault downstream the line, and if we don't detect here, we can detect in the second section, and we can go up to different curves of faults that they are studying protection. Then we do have the differential protection, where basically we measure two different ends of the line. And by measuring two different ends of the line, we know that by basic Kirchhoff law, energy or current that comes in is current that comes out if we consider as a big node. So from this definition, we can actually identify if there is a fault because the current coming in is not the same current as coming out theoretically. So due to this, we can compare in a line, and we call protection object, which can be distribution line, it can be a transformer, it can be literally anything between the boundary, and we can measure and protect them over if there is a ground fault or basically any type of fault. Here I'm showing a little bit of the algorithm, the diagram. Then we have the distance protection. Distance protection also is used most common in transmission level. Nowadays, I mean, differential protection, distance protection, and directional relays, most of them they are used in transmission level or distribution substation medium voltage level. And the common one over current protection is the use in low voltage. But as I showed before, like with the penetration of inverter-based resources, we need actually to address different types of studies because we do have different types of operations now. So in the distance protection, we basically, based on the distance, we can identify where is the fault. And here we use now the CT and PT to either for measure voltage and currents. So we can identify by the impedance, basically, where is the location of the fault if it's a very longer line. Uh, and directional relays, basically, they do detect if we have a shift on flow. So as we mentioned, overcurrent protection doesn't consider directional relays because traditionally it goes from upstream to downstream. But now we have upstream and also downstream to downstream. So this open a big area of study for directional relays where we can actually identify faults and different sites of operation. And also the literature mentions about intelligent systems, which is MCC type of method, different adaptive techniques to change them through the different changes of the grid is experiencing. So this example, I'm showing the test case study model for a fault, for instance. And this is the same online diagram as I showed before. So basically, in the blue line, I'm showing how the power flow operates. So this is the pre-fault case. And we can see how the power flow is going from each inverter towards each load between the whole microgrid in this array. But suddenly, we do have a fault that happens in this point. If we have a fault here, our currents will shift. So we will see that the currents after the fault, they are different if the fault is not clear. So we can see that there is a change in direction on the right-hand side. So it goes from going right to left. That means we are feeding the fault. And this gives a way of analyzing the grid as a differential type of relay method that I showed in the previous slide. And this opens a new set of study for distribution grids. So based on that model and the case I presented, we were able to identify a few study cases. I mean, Jerome and Sergi Yaremes is the person who actually identified with Professor Viresh and Dr. Ravich, and we could able detect how the fault happens. So through a simple algorithm where we just test how the current, we measure the current in the different ends. We do the asymmetrical positive sequence co uh, conversion of the signals, and we pass actually from the ABC regime to the phasor regime. Here we can implement a full cycle discrete Fourier transform where we have basically 10 or 20, depending on the sample frequency we're utilizing. Our models we utilize 1,200, 1,000, and we tested based on standards to know different type of switching frequencies, and also for the relays. So we can basically have like a moving window where we can update by the recursive of phasors or the recursive full cycle DFT, where we have a full cycle either in 60 hertz or 50 hertz. And we can be changing, so the last measurement goes out and the new measurement comes in. So we move in this way to improve the speed of the calculation, so be able to detect in real time if we do have a fault event or any disturbance in the operation of the on the distributed generation or the microgrid. So the first method implemented, basically we obtain the phase angle, so we calculate the phasors, and we identify the cosine of the angle. So we were able to identify that when we have a fault, we have a shift of the current. So that means the positive sequence cosine of angle changes direction, and that means creates a method for detecting from passing from positive into negative or either negative to positive per unit, because it's cosine factor. Maybe some people will think it's a power factor, but because we are using the positive sequence, we decided to keep it as a per unit and unit-less system. And as we can see, this is measurements in the both ends of the line. So the blue line is showing the left-hand side end, and the orange one is showing the right-hand side end. And we can see that when there is a fault, we can able detect through this algorithm. Then the second method we implemented is the model based on a broader communication system in case the cosine won't detect specific cases that we were able to face in the daily life. So this system includes a bigger communication system. So actually more devices are connected additionally to the original ones mentioned. And we tested basically the slope over 2 cycles, and we tested the ROCSP over 3 cycles. So I will explain this a bit later in the following slides. But basically, as we can see, when we have a fault in 0.5 seconds, due to the disturbance, we can able to identify a fault, which doesn't happen in normal operation. So the first method shown here, basically we have a three-phase current. We pass to a recursive DFT. We obtain the positive sequence. We obtain the cosine function of the phase angle. We decide either it's positive or negative, and by this comparison, we can trigger a relay to identify if there is a fault or not, which is shown in the bottom figure at 0.5 seconds. On the left-hand side, we see that there's no trip. That's why I won't explain too much here due to the time constraint, but the method, we call it the rate of change of positive sequence cosine of angle. And in this figure, I'm showing two different relays point of view. Like in the distribution line, we measure from two different ends. So we are detecting from each other end how is each relay seeing or each device seeing the fault within the grid. So we can see that when we have a single line to ground fault, we see actually a disturbance, and the fault, it can be detected. When we have a double line to ground fault, also 0.5 seconds, we see a disturbance and the change of the current, and we can also detect to the fault. So here I have a trip. So here I implemented actually the trip mechanism with the time delay, how long it takes tripping for showing the response and results. And on the bottom figure, I'm showing the double line to ground fault case. So here I'm testing 3 faults. The triple phase is trivial, so I think it was it's detected as well, I see, but these are more critical cases, I think, so these are more interesting to see. And we can see how our logic is fulfilled, like either we change from positive sign to negative, and the fault can be detected. So this is how we see from relay 1, these 3 faults, and this is how we see from relay 2, these other 3 types of faults. Then we have the second approach or method where we implement, basically we do the calculation of the 3-phase current, we do a recursive DFT full cycle, we obtain the positive sequence, we calculate the slope at the arrow COSP. Those are the 2 methods we use for detecting. The slope is the rate of change of phase angle over a cycle. The arrow COSP is the rate of change of the slope of the angle over a cycle. So here we utilize three cycles measurement, so it shows its robustness of response. And for the slope case, we utilize only 2 cycles. It's still robust, but we wanted to check to go a bit farther to the to be able to handle critical loads. So basically, we have a threshold limit identification, and by comparison, we can trip or not trip the fault. In the following slide, I'm showing the different type of cases, which is the line-to-line ground, single line-to-ground, and double line-to-ground, how seen from different ends of relays. And as we can see, the fault can be identified by the slope method, and also for the single line-to-ground fault, and from the line to ground. So usually we use a threshold here, and threshold here we utilize is the frequency of the grid. And as we can see, all of them pass the threshold. Now a critical test is the tap load. So tap loads, they are in between a distribution line. So they might go and might not detect it. So that's, I mean, the big question. So by implementing the 2 methods we tested, being the first one, the bottom one, we can see that actually when we have a fault, we have a discrepancy in both ends of the line. But they is not big enough to cross the zero boundary and be detected. For the second method, the arrow CSP and the slope of the angle, we also can be able to identify that there is a shift. We can see the response. We can see that it overpassed the restriction, as I said. But for instance, here, I mentioned the threshold will be 50, which is a grid nominal. So in here, it won't trip, which is okay because it's a tap load. It's not a fault. It's not necessary to trip. So we can validate that the systems were operating for different cases. And the last section shows about communication and fault clearing times. So basically, we know that in communication there exists a transmission line delay, and we have communication delay, we have the relay operation delay, and the transmission delay latency, which we're able to trip a circuit breaker when there is the sign of tripping. So here we are showing when actually a fault happens and one is seen by each of the different relays and when actually will be tripping. So we can see that it trips between the margin that we were expecting. So it takes for the communication 20 milliseconds, for a relay delay 20 milliseconds, and for the latency time will be another 2 milliseconds. So the bottom here is showing the communication delay, and here is showing the relay delay, how it's shown in different steps between the block diagram. And here I'm showing actually the effectiveness of this method by showing a test case of a fault and an auto trip of the relay. So we have a fault at 0.5 seconds. I mean, in this case we tested double line fault. I'm showing the voltage and the current. Once we have the fault, it goes through the algorithm and goes detected. Then it goes to the communication lane, to the tripping signal, until it reaches the circuit breaker and is able to open the grid. We have this time gap, which is a faulty operation regime. And we can see that when the fault is clear, our grid is operational. So in this case, we opening the line, so we still feeding the grid by the different other lines. Or we are removing the fault, and the fault is clear, and then we can return to normal operation. This is what we wanted to test. So we know that a fault, it takes 0.042 seconds and clearing the fault. And I think by this I will come to the culmination of my presentation. As a recap and important conclusion, I think we have that we were able to validate every single step of the modeling. we try to be very minutious and to check even the small detail to try to match a real life case study, even though we're fully focusing using a simulation, which is MATLAB and Simulink. So we tested and compared responses with inverters, different distribution lines, and different transformers, and the integration among all of them into different voltage levels. We implemented the drop control for sharing the load without communication. It's a very efficient way to communicate between inverters and all of them that are voltage source type of inverter, which is the common one we can buy in the anywhere. We were able to test how the frequency and the voltage is kept as the norms expect us to do it. Disregarding we have a load, disregarding we have a fault, or when we turn to normal operation and we follow the critical times. We tested all the possible faults that do exist in the grid out to our knowledge, and we create a different type of relays that for operating in the microgrid, which is a differential type of structure where we can compare actually two ends of the line. And so we use tableaus to differentiate how a fault is different than a tableau, even though we follow the same algorithm, that now the energy who's flowing through is going out, the one in out will be different. Also, we show that these relays implemented, they can operate in a different subset of all these grid, and even though it can be scaled because of the construction of the microgrid. Thank you everyone for your attention, and if you have any question, please let me know, or something you would like me to clarify better. Sorry if I have rushed a little bit, but I was trying to point out the most important thing on every single slide. Thank you.
Thank you, Jorge. This was a great presentation and the detailed discussion. I see one hand raise. I think they can unmute themselves and ask questions. Money, you'd like to go? Money, do you have a question? I still see you as muted. Any other?
Oh, no. Can you hear me?
Yeah, we can hear you now.
Okay. My question is, the presentation is very detailed, very nice, but when it comes to classical distribution system protection, that is not changed at all. And I'm not trying to make a pitch for the book we just released from Wiley and IEEE, and that one covers very in detailed classical protection. So I just want to make sure people who are working in the field for new, this is not, it's a more like a, what you call a review or something. So I know you spent a lot of time. I appreciate it, but anyhow, I thought I will make that comment. And but it's nice that people have courses in distribution systems that were not there even 10 years ago or so on. So it's just a comment I'm making, saying that people who are in this field, younger people who are in the field, should not think that classical protection has changed anything. It's okay. Did I say things right, Miroslav?
You did, and it's not the intent of Jorge's presentation to attack classical distribution because it's by far prevailing everywhere. It's focusing on microgrids, which are in some cases connected to the feeders and require different approaches because of these situations that he has described. So you are quite right. When you look at the percentage of use, classical distribution protection is not going anywhere.
Yep. Anyhow, I just thought I would make that comment, and I appreciate your comments, Miroslav. I know I have to learn a lot. Thank you.
Thank you,
Yeah,
Manny.
I see one question in the chat from, does the DG model can source zero sequence currents? How the performance of production scheme is guaranteed in such case?
So I'm not sure if I get it right, the question, but
Can you read in the chat? Maybe that might help.
Yeah, give me a second. Does the DG model can source non-zero sequence currents? So our our inverter specifically, it's constructed using the DQ0 transformation. We have a decoupling algorithm. So we do study the D and Q independently. I'm not sure if that's the question he was asking for. And also how the performance of the production scheme is guaranteed in such cases. So
Yeah.
due to the decoupling algorithm, we can able to study D or Q or zero, I mean, but D and Q mostly to avoid further down the line, which this is different than the positive sequence, negative and zero sequence that we utilize when identify the relay. I mean, both have two different control systems. One is the inverter as itself, and the relays as themselves as well. Different construction. I'm not sure if that's answered the question.
I hope yes, because I didn't see any.
Oh, yeah, he wrote
other
yes
questions.
in the chat.
Yeah. Yeah, I think we passed the 4 minutes. Thank you, Jorge, and thank you, Viresh, for presenting this webinar. I really appreciate your time and efforts. Okay. I also thank Professor Miroslav behind the collaboration of IIT and the TAMO. Okay,
Thank you so
that's
much
for today, and then we look forward to see you in the next webinar. Thank you. Have a good weekend and good rest of your day.
Thank you, Professor Sanjeev. I appreciate your words.
Thank you, everybody. Bye-bye.